There we go. Good afternoon. We should see people start coming in. Yeah, it takes a little while once I open it up for all the attendees to come in. So we'll give it a minute or two while we're waiting. Good afternoon, good morning, good evening, wherever you're coming from. This webinar had something like 77 people registered. So we usually get about 40 to 50% of that attend. So it'll take a while for all the attendees to come in. Before we get started, we don't run these like regular classes, so it's not two-way audio video. This is much more webinar style. If you want to ask questions, you can ask questions in the chat. I think there's a Q&A, but I'd rather just use one thing, so the chat's probably the way to go. And let me just use that chat right away. I'm going to put my email address in there just so that you have it if you have questions after this session today. You can ask those questions in there. So hopefully you find the chat and you can grab my email address from that. I'm still waiting for more attendees to come in. But while we're waiting, I just wanted to sort of introduce myself and our company. My name is Miles. I work for a company called ExitCertified. If you're not familiar with ExitCertified, we are we've been in business for about 23 years, something like that. Mostly partnered with large vendors like Amazon, and so especially cloud training, we're partnered with Amazon, with Microsoft Azure, Google Cloud, Oracle Cloud. And then beyond that, companies like IBM and VMware, large companies that have, usually certifications and a training program, and they come to us to help them scale, especially in North America. And about a year ago, we got acquired by a sort of private equity company that was putting together a larger instructor-led training company. And so now we have these sister companies, Accelerate and WebAge Solutions, and each has their sort of sweet spot of what they do. WebAge does a lot of sort of upskilling programs. If you have a bunch of new hires and you need to take them from straight out of college to become data engineers or data scientists or even Gen AI engineers, something like that, we do 4 or 5 week, 6 week programs to get them, really ready to be project ready. And so this really increased the range of the kinds of things that we can do. I mentioned my name's Miles. I've been an AWS instructor since 2014. That's when ExitCertified first partnered with AWS. I taught our first class in June 2014. I just looked it up because I got my 10-year anniversary. But I'd been using AWS for a little bit before that. I started off as more of a database developer. And then when Hadoop came out, in the mid to late 2000s, I kind of started using Cloudera's distribution quite a bit. And that's what really led me into the cloud. I now teach a little bit of Google Cloud and a little bit of Oracle Cloud as well. But AWS is really my main area of expertise. I'm actually not teaching all that much these days because I help out on our sales side when they get into the deeper technical discussions with customers. And so I'm doing a lot of those sort of subject matter expert calls. But that's just a little preamble before I jump in. I'm going to just end those slides and I'll go grab the actual AWS slides. So these discovery days are, they're all about 90 minutes. So this should go from 1 till 2:30-ish. And AWS says, we're going to give you the materials. And, as long as you're an authorized AWS instructor, you can deliver these for free to your customers. Right? Now, we are able to record them now. And so you should get anybody who registered, including the people here that have attended, you should get an email probably tomorrow with a link to the recording of this. The one thing I can't provide you with is the slides. So Amazon said, no, you're not allowed to share the slides. So you'll see the slides here. You can look at them again in the recording. And so that's what we have available to us. As I mentioned, before everybody got in, if you have questions, you can throw them in the chat. The chat just goes to the, hosts and panelists, which is, I think, just me on this one. And so I'll get to your questions, as soon as I see them. I've got the chat kind of sitting there while I'm teaching. I kind of look at it a little bit. Um, and so let's talk a little bit about this. This is kind of the fourth in our series of webinar Wednesdays. We've done a couple just on the basics of data analytics, a little bit about the analytics stack, and then today this one is really on purpose-built databases. And we're going to see that in AWS there are a lot of database services. There's a couple that have to do with relational databases that are wildly popular. And then there's a bunch of NoSQL databases. And we'll talk a little bit about that term and what does it mean and sort of where did it come from and why something new. Relational database has been around since the 70s. And so that means we've got 40, 50 years of knowledge on how to design them, how to tune them, how to query them using SQL, right? And so the real crux of this hour and a half is going to be, why do we need something new, right? If it ain't broke, don't fix it. Well, there's places where it maybe is broke. And so there's definitely some situations where relational databases aren't going to handle exactly what you need them to. And so this is where we started to look for alternatives. Right? And so that's what we're really going to get into and try and decide on a case-by-case basis, here's the requirements I have. Here's the nature of the data. Here's the nature of the application that's going to be using the data. What would be the best tool in my toolbox to use? And so that's what we're going to talk about here. Now, this is sort of an hour and a half version of, basically a planning and designing databases class that I'll tell you about at the end of the course. And so I'll talk about some promotions at the end and upcoming classes if you're interested in taking a longer, 3-4 day class. And we also have a couple more webinars coming up that are free in the next couple Wednesdays. So I'll let you know about those as well. Mm-hmm. So here is what we're trying to do is really understand the databases and what makes a database well architected and get into why to use these purpose-built databases. And once you figure out how to use one versus another, let's try and analyze a workload requirement and choose the right model and then choose the right purpose-built database. So you don't have to be working with AWS too long before you run into this concept of the well-architected framework. This isn't something that was initially there, way back in 2006 when AWS first started. It was very much, an idea that came because Amazon was getting people complaining about things and saying, hey, I'm using your services, go and look at my architecture and tell me what's wrong. And so, there is this idea if you've got, a high level of support with AWS, like enterprise support or something like that, you can have them do a well-architected review of your design, your architecture of your cloud solution. And they'll pick it apart and tell you what's wrong with it. But what they did was they said, well, all those questions that they ended up with this huge list of questions. How are you doing this? How are you doing that? How are you doing this? Have you thought about this? And basically they said, well, instead of us having to do the well-architected review, why don't we give you, here's the main pillars. Here they are. Here are the main pillars of the well-architected framework. And then we'll give you a white paper for each one where we kind of outline, some best practices. And here's the questions you should ask of yourself when you have a prospective architecture, right? And so, when we look at it just through the lens of like the database side of things, when we're looking at operational excellence, what you're really trying to figure out is, what are ways we can improve operations of our database? Are we using optimal maintenance windows? Are we proactively monitoring the right metrics and logs? Are we using those metrics to kick off, alarms to tell me of things that are maybe, not going well operationally, right? Are we looking for some sort of automated corrective actions when those alarms go off? When it comes to reliability, this is where you're focusing on your workload to perform, its intended function correctly and consistently. So we're looking at things like, Is it a resilient architecture? When something goes wrong, do we have replicas? Do we have multi-AZ deployment? Do we have backups and all those kinds of things that we would want to make sure that this database is going to be reliable, right? When we get to performance efficiency, this is sort of making sure that our database is, when we plan and design it, we want to make sure that we're using the right service to meet my needs, that we've picked the right database and services based on access patterns, and the right data storage based on what kind of data is coming in and all that kind of thing. So just making sure that we have the right thing. And then cost optimization, that's one that's, I think, across the organizations that, customers of ours, we've seen that become a lot more focused lately. Early days when people first moved to the cloud, they were just sort of, hey, I want to get to the cloud. I hear I'm going to save money, right? And then a couple of years in, they're starting to look at their cloud bill going up and up and up and saying, well, now we need to focus on, are we using the right services? Are we using using them in the right way that we're saving money? And so there's lots of places where you can look at cost optimization and say, do we have auto scaling so that our database responds to changes in demand without having to over provision things, right? If I look at my database and I say, the CPU of this database has never gone over 2% over the last 6 months, it seems like maybe I'm paying for too much CPU, right? So I can try and right size that. That's a term we use in the cloud where we say, I maybe started with a lift and shift, and we said, look at what we have on-prem. When we move to the cloud, let's launch things with the same kind of CPU and RAM and storage that we had on-prem. But we may have been drastically over provisioning on-prem because we buy hardware every few years, and so we have to plan for way ahead. In the cloud, because we can add things pretty quickly, we can react as things change, then there's no need to really over provision for years ahead. You're really just paying for resources that are sitting idle, maybe, right? And so there's a lot of that goes into the cost optimization. Also, another part of that is, total cost of ownership isn't just what my bill is, my monthly bill for AWS, but it's also how much time do we spend our employees on administration and all that kind of thing. So a lot of times a move to something that's serverless versus having to manage, a cluster of Linux servers and patching them and, all that kind of work that has to happen, that could be a way of doing cost savings as well, is where we take some of that administrative burden off our shoulders and let Amazon deal with it. The sustainability part, this is kind of a newer pillar that they added in. Not every company is focused on that, but a lot of large customers really are, right? Trying to focus on the environmental impacts, especially energy consumption and efficiency, right? So when it comes to a database, again, a lot of the stuff that we do to try and minimize cost optimization, not paying for machines sitting idle, that helps with sustainability. But also, things like data movement across networks, storing data closer to the customer, to the consumer of that. We got a database and then the applications that use that database. If we're not moving data around, that actually helps a lot with energy consumption. Okay? So there's a lot of things we can do to reduce that. And then finally, security. I mean, security is a wide-ranging topic. I think I've got a slide just on that, security. Yeah. So this is some of that security pillar. When it comes to databases, well, just across the board with security in AWS, we often talk about what we call the shared responsibility model, right? And the shared responsibility model is this idea where, some of the burden of security falls on Amazon's shoulders. Of course, they're taking care of the physical on-prem data center kind of thing. And then some of it falls on us. And so trying to figure out whose responsibilities are what, understanding that is important. Data protection and compliance. So data, we want to make sure that our data is secured so that people can't see it or change it unless they have permissions to, right? And so there's sort of two times when we have to worry about data: when it's in transit across a network and when it's at rest. And so we have different controls for both of those, right? Another part of the database is, when I connect to it, I usually have a username and password to represent a database user. So I don't want to hard code those things in application code somewhere, because then any developer who has access to that code, or anybody who gains access to that code, could go and jot down that username and password and then use it outside of that app to do something they maybe shouldn't be doing, right? So there's different ways to store and use secrets in a nice, secure way, so that we don't have to copy around these credentials all over the place in code, right? Um, it's interesting when we talk about databases in the cloud, there's usually kind of two sides of that username and password kind of thing, because there is what database users are allowed to do something inside the database. So say we're thinking like an Oracle database or Microsoft SQL Server or MySQL, Postgres, whatever database you're used to. You got usernames and passwords inside the database, and then you've got permissions. Okay, this person's allowed to, create tables. This person's allowed to, look at these columns of the table, but not these columns. You can get that granular, right? In AWS, we have all those database permissions, but then outside of that, we've got AWS, API permissions. Who's allowed to launch an RDS database? Who's allowed to delete a DynamoDB table, right? And so these things are not inside the database. These are AWS API calls. And so they're really governed by a slightly different set of authentication authorization. And that comes down to something called IAM, AWS Identity and Access Management, because that's how we determine who's allowed to do what with the AWS API. Mm-hmm. I guess last thing I want to mention here is the network side of things. When we launch a database, we're very often, and not all databases have to be like this, but most of the time we're launching it into a network, and then there's all sorts of network controls. What ports are open to who? And we've got this idea of a virtual private cloud and then subnets inside of that. And we've got one type of virtual firewall is at the subnet level. So at a networking level, we've got these network access control lists, or NACLs. And that says what kind of traffic's allowed in or out of this subnet. And then actually, when we launch, say, an RDS database, we also have another kind of virtual firewall called a security group that just says, by default, there's no ingress to, this firewall. We have to go and poke holes and say, okay, well, this is an Oracle database. It's listening on port 1521. So let's open port 1521 in this security group too. And then I determine what other security groups is allowed, so where are my app servers or maybe my web servers that need access to this database? And so there's a lot of like networking stuff that comes in as well. Now, we're not going to go too far down that hole here, because I don't suspect you're all networking administrators. Yeah. All right. So let's really get into this idea of purpose-built databases, and we'll keep those sort of pillars of the well-architected framework in the back of our mind, and we'll try and revisit them as we go along. Right? And we're going to take a look at how these purpose-built databases have transformed how we do database solutions. And we'll start with sort of traditional applications, traditional databases, which is really relational database. Right? If you think about traditional apps, you have sort of point of sale apps, or the back end of a website, or CRM, payroll, traditional kind of applications where you might have hundreds or even thousands of users inside your company using this database. And you may have gigs and gigs of data, maybe even terabytes of data. And it's all sort of inside your headquarters of your company, something like that. And when somebody comes in and runs a query, hopefully the query comes back in a second or two at most, right? And we could have tens of thousands of requests coming in per minute, per second, whatever, depending how many users we have. But, this is the kind of traditional databases that we used, and we used relational databases for this. And in the old school, like before we got into cloud, the economics was all pay up front, right? Go buy the hardware, go buy a license from Oracle or whatever database vendor, set that up, set up your storage, and, you could scale vertically. When we talk about scale, vertical scalability is saying, I bought this machine, can I add more horsepower to it? Can I add more CPU or more RAM or more storage to it? Right. And so, when you go way back to the 70s when relational databases first came out, it was the early 70s when, Dr. Teddy Codd wrote this white paper about how, he was sort of a mathematician. He used mathematical ideas to come up with normalization and how a relational database would look. And it was really the late 70s when Oracle came out and then DB2 and from IBM and some of these other kind of commercial databases started to really take off in the 80s. But they were all kind of designed to live on one physical machine. And so you could go buy more powerful machines. But at some point, when you got into the tens of thousands of users, all of a sudden you're starting to buy really big, expensive machines. Now, the thing that changed everything is the internet, of course, right? Once you open up an application and say, I can have millions of users at once, that's sort of a different animal, right? So now all of a sudden we have a million plus users and around the world. And the data volumes can start to get really, really big, right? So not just terabytes, but petabytes, even exabytes. Mm-hmm. And a lot of times what we're doing in the web, like I've got some sort of a database where I need to be able to query my data catalog very, very quickly. And so this idea of responding in a second or two is unacceptable. I may need millisecond or even microsecond latency, to be able to return responses. You can imagine if you go, when you say you're on Facebook or something and you see an ad that's being shown there, that ad, there's a whole auction that goes on in the background to say who's willing to spend the most to show an ad to, Miles, who's got these demographics, right? And so that there's a whole auction that has to happen in, a couple of milliseconds where we have to figure out, okay, who's willing to, okay, and what do they want the ad to look like? Maybe based on my history of what I've done with that company, all kinds of things. So we need to be able to access data very, very quickly to be able to handle those kinds of things. Also, when we get into not just mobile apps, but Internet of Things, you've got a sensor. If you go to any manufacturing plant now, every piece of equipment has all kinds of little sensors that are firing every 100 milliseconds, mm-hmm. and they're saying, okay, just spitting out a little chunk of text that says, this is my sensor ID, here's my reading and the date and time, right? And we don't have time to go and store all that in a relational database and then run queries on it. We need to be able to access that information really fast and make some quick decisions to say, uh-oh, something's going wrong. Let's stop the production right now before, we blow some machines up. And so very different kinds of animals, right? And so the economics, when we do this in the cloud, is maybe more pay as you go, right? I can build an application that scales not just up and down, where vertical scalability, we're adding more horsepower, but maybe more importantly, adding more machines in parallel, right? So if you think about just a web app, if I can handle, X number of users on one web server, well, then I'll go and get 10 web servers and put them behind a load balancer. And then where am I going to store all the data for those? Well, on a number of machines, and maybe that number of machines needs to be able to grow and shrink. And so, we'll pay in the cloud for those things as we need them, right? And so this is a little bit of how things have changed over the years. Doesn't mean we don't still use traditional applications and traditional relational databases. We do, but a lot of times things have changed. Another big change over the last, say, 10 years is that most people are looking at really big, what we used to call monolithic applications, and we're breaking them up into little smaller chunks, what we sometimes call a microservices architecture. Right? And so here's an example of one. Now this looks completely serverless to me. I can have kind of a static HTML website, and I just store that in S3. So I don't even have to run, a bunch of EC2 instances running like Apache or whatever web server. And when I click on things, I've got some JavaScript there that says, hey, when you click this button, okay, we need to go call some back end logic. Well, instead of that back end logic being a bunch of web servers, I can just encapsulate that back end web logic, business logic in a bunch of serverless Lambda functions. And then we can front that with an API gateway where we say, hey, if they're coming to this URL and a get, call that Lambda function. If they're coming to this URL and a delete, call that Lambda function. Right. So it's a nice serverless way of setting up a web interface to my backend business logic. And then each of those Lambda functions need to go in, store some data, get some data from somewhere, a little more permanent. Well, in the old days, we would just talk to a relational database. But relational database is just, it's good for certain kinds of access patterns, not for others. And so when people start to go down this road of microservices, what they'll end up doing is they'll sort of change how they develop their teams. They'll say, okay, well, let's make these small cross-functional teams. Back in the early 2000s, when Amazon did this, they took their big monolithic app, they broke it up into thousands of what they called primitives. These days, we would call those microservices. And then they took their teams where they had a bunch of developers and some testers and administration operations people all on different teams doing different things. They said, no, we're going to make small cross-functional teams. Let's get 3 or 4 developers, 1 or 2 testers, a couple of, 1 or 2 operations people and a project manager, and we'll make this team. And this team will be in charge of, a small set of microservices. And they'll take it all the way from, building a roadmap, gathering requirements, designing it, implementing it, testing it, putting it into production, and maintaining it there and fixing bugs and everything. And so this team, it shouldn't get too big. At Amazon, they decided, maybe 8, 10 people tops. So they called them 2 pizza teams. You could feed them with 2 pizzas, And so, you were in charge of these microservices. And one of the kind of concepts that came out of microservices architecture, it's kind of a funky name. They call it polyglot persistence. It's the idea that, each microservice has different data storage and access needs. So why not let them pick what's the best tool for the job? Because what we're going to do is, all the other applications, they don't know how this one function is storing its data. So if the best place to store it is in a relational database, great. If it's in a key value store, great. If it's in a document style or a graph database, great, right? And it doesn't matter because we're not going to open up all these different backend data stores to the world. If you want to access some of the data in this DynamoDB table, what you're really doing is making a call to the microservice. If you want to know about the orders, you go to the orders microservice and say, get me all the orders like this, or, go place an order, or, change the status of this order. And so I'm able to choose whatever tool I want to store the data in my microservice because I'm not exposing that to anybody else. I'm just exposing, this is my API. Here's the things you can do with the orders microservice. Here's the things you could do with the sales microservice. And so that really kind of interesting. What it does is it says, hey, that really opens things up. Now, some companies don't love this because, what if somebody wants to move from one team to another? And I was on a team that was using relational databases. Now I get moved to another team and they're using, document style database, MongoDB, something like that. And you're like, oh, now so, in certain companies, you might say, okay, well, here is the set of different, purpose-built databases that we use. You may not want to open it up to everything on Earth. You may want to just break it down to just the AWS ones or just these open source databases, right? Just so that we can kind of limit the list of what you might run into in our corporation, right? So, so here's sort of, if in the ideal world where you have everything at your fingertips, you're going to look at the workload and figure out, as far as the workload goes, like are we doing, does it need transactions? What's the nature of the querying that's going to happen? Is there ad hoc queries, or is it kind of canned what we're going to be doing with this data? There's a bunch of things that go into that, and we'll look at that. And then you choose what's the right model. Do I want a relational database or a NoSQL database? If it's NoSQL, which kind? You know, and then we go and choose what's the right purpose-built database for it. Right? So which AWS service do I want to use? So we're going to start with that first step, analyzing the workload requirements and try and come up with what are all the things we should be thinking about when we're doing this. And so we got a bunch of slides coming up on this. So that's where we're going to start. We've got sort of, what are the application characteristics? And we got a slide, I think, on each of these. So this is just sort of a quick overview. So what are the application characteristics? What are the requirements as far as availability and durability? What kind of performance do we need? What's the capacity and scaling? What do we expect down the road? Okay. So let's start with the application characteristics. One of the first things you run into is this sort of an online transaction processing or an online analytic processing kind of thing? Now, if you haven't heard those terms, if we go way back and we think about the early days of databases, you had Oracle and DB2, and then a bunch of others came along. And they were all kind of built the same way. They were built for what we call online transaction processing. So, the classic is a point of sale system. We got customers who place orders for products, and you need to be able to, query and look in the catalog, find this product. You need to be able to place an order for a customer. You need to be able to look and see what are all the orders this customer placed, all that kind of thing. What we're normally doing is single row insert, update, and delete in a relational database, right? So when I place an order, what are we doing? We're inserting a new row in the orders table. When a customer changes their address, what are we doing? We're updating one row in the customer table, right? And so there's a lot of like single row insert, update, and deletes. And then when we query, we're either querying maybe just one row, like go find me, order 101. I need to look at the details for it or whatever. Or maybe a small percentage of the table, like find me all the customers in the Northwest region, something like that. So that's your sort of regular online transaction processing, and traditional relational databases are really designed nicely for that. They are row oriented, right? When I insert data, we're inserting one row at a time, and they find some contiguous space on disk for that. Right? Well, what we started to find was in the 90s, people started to do a lot of bigger data analytics kind of queries. They're trying to say, look through the last 10 years of my orders, find me the customer who's placed the most orders. Or, find me the total sales in the Northwest region, right? So we get into those kind of queries that are maybe full table scans, right? And if you're using a traditional relational database for that, you're going to get a call from the DBA saying, why are you crippling my database with these huge queries, right? And so what we end up with is there's sort of a lot of contention, right? Because we've got our regular online transaction process stuff happening, and it's all based on row level. So, I'm doing one row at a time, sort of transactional stuff. And then you've got these huge queries that are trying to do full table scans. And they're very much at odds with one another. So in the 90s, what we decided to do to fix this was to say, well, let's just use two different databases that are tuned for different things, right? This was the birth of data warehousing. And so my first job out of college, way back in 96, I was working for a place that, we were in transition. We had been doing mainframe. We were moving to more of, client server type stuff. And we had an Oracle database, and that was our online transaction processing thing. And then we said, let's make just another Oracle database to be our data warehouse. And so what we did was we went and every night we ran a job that would grab, okay, what are all the new transactions today, all the new rows that got inserted? Let's go extract those, transform it, maybe summarize it a bit, and load it into the data warehouse. And the data warehouse was just another traditional relational database, but it was tuned a little different. The tables were sort of denormalized a bit. You may hear people talk about a snowflake schema or a star schema. These are some of the different kinds of ideas that you have in data warehousing. But really what we're doing was we're saying, let's use a database that's more optimized for a bulk insert every night and then huge queries all day. Right? And so we have a database separate from our transaction one that's all single row insert, update, deletes, and small queries. And so that's sort of the online analytic processing. And so that's sort of, when you think about the difference between these, one is traditional relational database, the other is more of a data warehouse. And if it's a relational database, these are some of the ideas that we have, data warehousing. What about caching? Sometimes we can't wait for something to go and grab it from disk, load it into memory, and then, sift through it using SQL, execute that SQL, go grab the data from disk, bring it into memory, send it back. So data that we're using quite frequently, we may cache in several places before we even get to the database. Right? So these are some things to think about. So sometimes the data usage lends itself more to a non-relational database. And so, like I said, relational databases started in the 70s, were fine until the early 2000s when people started to complain and say, there are some things that relational databases aren't great at, right? And we started to talk about big data, right? That became a real buzzword in the mid to late 2000s. And the big data problem, you think, well, it's just too much data, right? That's just one element. Sometimes you talk about the 3 V's of big data: volume, velocity, and variety, right? And one of the things that we find is relational databases, because they were designed to live on one physical machine, at some point you got too much data to live on one machine, right? And so most database vendors figured out a way around this. They said, okay, well, let's take rows A through M, put those on one database. Rows N through Z, we'll put those on another, right? And what we do is we call it a clustered database. So in Oracle, we have Oracle RAC, real application clusters. In MySQL, you set up MySQL cluster, right? And so it's really becomes kind of like a pain as far as administration goes, because we got to figure out a workaround to this problem of too much data that lives on one machine. But those are patterns that we can figure out, right? So that sort of can solve the volume problem. But what about the velocity and variety problems, right? One of the things that happens when you have a relational database is you start with a create table command. And you say, create a table called this. And by the way, here's what all the columns look like. So when you create the table, you need to know, what do the columns look like? How many columns? What are we going to call them? What's their data type and size, right? And then every time I do an insert, what the row I'm inserting had better fit those columns, right? If at some point we realize, oh, I've got a new column, I could go back and do an alter table command, right? Every relational database has an alter table command where you can add a column. They even have ones where you can remove a column, but you can imagine that's a little bit stressful, right? Especially if in your code you've written a bunch of select star from this table, all of a sudden now one of those columns is gone, or there's a new one that's been added, that's going to mess things up. But more importantly, in the middle of the day, if you're doing ad hoc data collection, if we just keep going and doing alter table commands, I got to lock that whole table while I add the new column. That means I can't do any insert, updates, and deletes while that's happening. All right. So again, we're getting that contention. And so what we find is that, the variety of types of data, if we don't know exactly what the data looks like when we create the table, we're headed for trouble. Or maybe the data doesn't fit well into the rows and columns of a relational database. So there's definitely things where we're just grabbing more unstructured data, and trying to fit that into a relational database is always a problem. Right? The other problem is the velocity. Right? Again, if we're just using one relational database, that if it lives on one machine, how many writes can you do per second to it? We're limited by that hardware, right? Now, if we have more than one instance of the database and it's distributed across multiple machines, it gets a little easier, but that's never easy to do in relational databases. What we found was that there was a new kinds of databases that started to pop up that were not relational, right? And we're going to see that list of all the different kinds of, what we call NoSQL databases. It's really an umbrella term. That term NoSQL got coined in about 2009 but some of those non-relational databases existed before, and lots of new ones have come since. And so it's really an umbrella term for things like key value stores, in-memory databases, wide column stores, graph databases, document style databases, right? And the list goes on and on. But most of these came after the internet existed, right? And so they thought about that internet scale and the possibility that we could have millions of writes per second happening. And so these databases were all designed from scratch to be distributed across multiple machines in parallel. So we can write to multiple machines in parallel. And a lot of them don't have that same upfront, tell me what the schema looks like for this table. They're a lot more loosey-goosey with, what do the columns look like? And you may just say, well, there are no columns. It's just a chunk of JSON. That's what a document style database usually looks like. I'm going to give you a chunk of JSON. It might have 10 child elements. It may have 12. Who knows? Right? But we'll deal with that in how we access the data. Right? And so there's a lot of things that lend themselves better to that kind of non-relational patterns. Things where we've got little IoT sensors firing. I've got thousands and thousands of these sensors firing every 100 milliseconds, sending me little chunk of JSON. Right? Application logs. I've got logs that are firing nonstop, and they're just like, here's a chunk of a log file. It doesn't fit well into the rows and columns, depending which kind of application, what kind of log. They may look different than other logs. Session state data, where we just want things in memory so that we can access them really quickly. So there's different things there. What's the nature of the database usage and the users? Is it a physical location? Is there network involved? How are we going to be processing this data? Are we doing it once every night in a big batch job, or every 4 hours in a big batch job? Or is there little bits of data coming in continuously, like IoT? Right? Well, we call that stream processing instead of batch processing. So these are some of the things we have to think about in the application. Mm-hmm. And so, as far as data access patterns go, first thing you would say is, what's the most relevant access pattern? Right? What's the main thing we're doing? So say we've got like a product catalog. The main thing we're doing is go find me product by, whatever, maybe the product ID, or by the name, or by the manufacturer. Right? And then subsequent to that, there's sort of add products to our catalog, update a product, maybe delete one. Right? Are the queries predefined, or are they one-time queries? Right? There's definitely things where, if you think about, if you got a web app and you've got a shopping cart, right? The shopping cart, we don't want to hold that in memory on the web server, because what if I have 10 web servers behind a load balancer? I want to be able to send any request to any web server, right? And so I can't have that shopping cart information just sitting on one of my 10 web servers. So what do? We move it off the web server into some sort of a database. Well, a relational database takes too long to query. We need more of an in-memory database. And if you think about it, all we're doing is saying, okay, I'm going to store session 101. Then later I'm going to come back and say, show me everything in session 101. And that's my shopping cart. So the queries are very simple. Get and put by primary key. We're never looking in shopping carts and doing ad hoc querying, right? So depending what the answer to these questions are, is it just read-only access, or is there write access as well? Are we accessing a single row or single item at a time, or multiple items, or all the items? Is there a key that we can use? Do we need the results sorted? And this will, push me to one of, yeah, I need a relational database with complex queries. Or no, I just need key value stores, very simple API, but I need massive scale, right? So again, it comes back to that volume, velocity, variety, right? Trying to decide what we need. Another thing to think about is transactions and referential integrity type stuff. Traditional relational databases where I've got, customers placing orders and stuff, and we got inventory, we might need what we call ACID compliant transactions. Certainly, if you think about like a bank account, hey, when I look at my account and I see my balance, I want that to be up to date. And if there's some other application that's either putting money into my account or taking it out, I don't want to see half of that transaction. When the transaction's done, if I query again, I should see the latest, right? So a lot of relational databases are used for this because they have this idea that a transaction is atomic. Even if a transaction is update this row in this table, update that row in that table, we decide that those two things go together. The two operations make up one transaction, and either they all happen or nothing happens. So we start a transaction, we make this change, we make that change, and then we commit. And either all the changes get committed or none. Right? And while we're making the changes, nobody's going to be looking and see half of the change and not the other half. So we might have this idea, and most relational databases have this idea of when I query the data, I'm seeing the before image. Even if there's some changes that are being made, until they're committed, I don't see those changes. Once they're committed, everybody sees those changes. So that's really what we call ACID compliance. And that was the traditional kind of transaction model that all these online transaction processing and all the relational databases had. Well, once we started to see these, distributed systems, we started to run into this problem of it's very difficult. We can't have, what's called the CAP theorem, CAP. We can't have consistency, availability, and partition tolerance. We can't have all three. That's sort of the theory. So it ends up becoming trade-offs of, well, if I need partition consistency, so if there's some sort of failure, if I've got this database running across 10 machines and one of the machines dies or whatever, I should still be able to look at the data, but I can't have 100% consistency and high availability. Something's got to give. And so what we start to see in these NoSQL databases is this concept of base. It's basically available, soft state, eventual consistency. Eventual consistency, that's interesting. What do we mean by that? Well, it means that when I make a change, if somebody queries right away, they may not see that change yet. After a second or two, if they query, they see all the changes. And that's because we've got this data distributed across a bunch of machines. When I query, I'm not looking at every machine to look at all the data. I may be just sampling it. And so I may not see all the most recent changes. And sometimes that's fine, right? If I'm looking at my product catalog and a product just got added and we don't see it, we query again, we see it, that's not the end of the world. And so there's a lot of situations where just easing up a little bit on the transactions requirements really gives us a lot better high availability and allows us to scale huge, right? And so that may be what we're having to deal with instead of full ACID compliance. Now, there's definitely places where we need that strong consistency, right? We need to have the most up-to-date data every time I query. And I want to reflect all the updates from all the previous write operations versus I'm okay with maybe I'm looking at a little bit of stale data, right? And so that's what you're going to have to decide. Now, some databases, if you look at DynamoDB, they give you both options. Strong consistency just costs more money because it's going to end up under the covers when you query. It's got to query everything instead of just a sample, right? So, that's the trade-off. Maybe eventual consistency or strong consistency versus how much money we're going to spend. Mm-hmm. I mentioned availability and durability, probably getting some terminology here. Availability is knowing that your data will be accessible when needed, right? So in the case of something like a relational database, if I want something to be highly available, what we're really saying is if there's a failure, I need a backup of that data somewhere, right? And not just a backup, but maybe I need redundant database running and a way that says, let's figure out if the database goes down, we'll automatically flip clients over to the standby database. And so they won't notice any downtime at all. Right? Durability is really knowing that your data will be there even when things go really south, right? So, if this whole region in AWS goes down, maybe I've been replicating all my data, to another region or the other side of the world. and at least I haven't lost my data. It may take me a while to get the application back up and running, but that's the concept of disaster recovery. But at least I've not lost the data, right? And so depending what storage we're using, what database we're using, we may get some high availability pretty easy, or even, like very easy. And the durability is usually if we're storing data at a region level rather than at an availability zone level, we get some pretty good durability. And then if that's not good enough, we'll do cross-region replication to another region so that if things go really south, we've still got that data. Right? Nice example of durability is we do have sort of an in-memory database that we can use for analytics. And what it does is it's an in-memory database. So when you access it, it's very, very fast, but it also stores to disk in case something goes wrong and we lose everything in memory. So it writes it out to disk as well for durability. But there, the availability is maybe the top concern. I need to be able to access that data really fast, but I also want to make sure that if something goes wrong, I'm not going to lose it. When it comes to performance, there's a lot of questions to be asked here. How quickly do users need a response? Am I okay with, in the order of half a second, 2 seconds, or does it need to be much faster, milliseconds or even microseconds? How many users are active at the same time? So what are my concurrency needs? How does the consistent response adapt at scale? So right now, we're expecting this level of requests. What if that request number doubles? Is it still going to be the same kind of response, or will it be a little slower? Right? I guess related to those ideas are capacity and scale. So analyze the past usage data to plan for future capacity needs. In the old days where we were buying physical hardware, capacity planning was very important. Right? You had to kind of look into the crystal ball and say, how busy is this app going to be this year, next year, the year after? And then you go buy enough hardware to handle the peak, right? And the peak, it's all guesswork, right? But you can kind of look at the history and make some guesses, right? You say, okay, well, we're an online retailer. Our busiest month is November because we've got, Black Friday and Cyber Monday. And, we expect to have this much. And then we go buy our hardware accordingly. Right. And so if you get the capacity planning wrong, you've either bought too much hardware and you spent a bunch of money up front that you didn't need to. Also, you have all this hardware plugged in, sucking power, heating up my data center, right? All that. In the cloud, because we can pretty quickly add or remove capacity, we don't have to do as good a job looking into the crystal ball, right? We can react much faster, right? And so we should be able to scale up and down. Well, when I say up and down, that's really vertical scaling, right? Adding more power, more horsepower to an existing machine. In the database world, vertical scalability is, it's fine for storage. We can add storage on the fly, but adding CPU or RAM, that's a problem. We probably have to stop and restart the database, right? Just like if I go and stick some more RAM in my, my laptop here, I have to reboot the machine for it to recognize, the operating system has to recognize that CPU, right? So it's not smooth, that vertical scaling, right? Scaling out is that horizontal where we add more systems doing the same thing in parallel. And if our framework allows us to just add systems on the fly, like if you're in a Hadoop cluster, you add more machines, they start heartbeating in and say, I'm here, give me data, give me processing. If you've got a clustered database, you may be able to add more nodes on the fly and say, heartbeat in, let me know about it, right? If you even just, web apps, you've got, 10 web servers, you add 2 more, they heartbeat into the load balancer and say, I'm here, give me more requests. And so we can very smoothly do that. We don't affect the existing machines and the existing workloads just to add more capacity. And you can imagine scaling out because AWS has, well, let's say seemingly limitless capacity. I mean, there are capacity limits, but no one of our customers usually ever runs into those, right? That we can just keep going. If whatever our framework is we're using, if it can be sufficiently parallelized, I can have 1,000 machines in a cluster, 2,000 machines in a cluster, right? and we can really do these huge jobs much, much quicker. Right? But maybe the most important thing is that in the cloud, we don't just talk about scalability, the ability to grow as our needs grow. We really talk about elasticity. What's the difference? Elasticity says I can scale out or scale in based on demand. Scale out when we need more, we have more requests than we used to have. Scale in when things aren't busy so we can save money, right? Because in the cloud, we're typically paying for compute, like however many virtual machines there are running, we're paying, so many pennies per hour for them. I don't want to pay for anything sitting idle. So in the middle of the night, when my database isn't busy, I don't want to pay the same as in the middle of the day when it is busy. Right? And so if this thing can grow and shrink, even within one day, when I'm busy, I'll add more capacity. When I'm not busy, I'll remove it. So I'm no longer paying for it. Right? So these are some things to consider. All right. Once you've considered all, what is the nature of the app, the nature of the data, then it's time to choose my data model. Right? And so think about what are the different kinds of databases that we have. And I've sort of hinted at a lot of these NoSQL databases, but it's probably time to do a quick look at them. Right? So first off, relational databases, this is, what we're used to. They have very good referential integrity. That means, you've got foreign keys set up in the database tables so that, when I place an order in the order table and I say, this is an order for customer 101, the database will actually look and say, go look in the customer table. Is there a customer 101? Yes? Okay, good. If there isn't, then let's not allow them to do this insert. That doesn't make sense. There's no referential integrity. Right? So traditional relational databases have referential integrity, ACID compliant transactions, and that heavy schema on write. We need to make sure that when you do an insert, it fits that schema. We're going to make sure this row looks like here are the columns and their data types and sizes. Right? But it's really good at doing, SQL queries that can be very complex. That's what we like about relational databases. Next up, we've got a NoSQL database called a key value store. Right? These things are usually set up so that it's like if I had a relational database, but the only queries I ever do are find by primary key. Right? I don't have complex queries. I'm storing the data and it's got some primary key. And when I query it, I say, go get me customer 101. Always the same kind of query. Well, because of that nature, we should be able to store it slightly differently so that we get really high throughput and low latency reads and writes. We're going to see DynamoDB is one of these key value stores. And it says, no matter how big the table gets, we could have millions and millions of rows in that table. When I do a find by primary key, it's going to take single digit millisecond, 3 or 4 milliseconds tops. That's very different than a relational database. As the table gets bigger and bigger and bigger, that index gets very bigger, then sifting through that index looking for customer 101 starts to take longer and longer, right? And so it's very low latency reads with endless scale opportunities with these key value stores. Next up is a document style database. So the first biggest one that I heard of way back in the late 2000s into 2010, probably when I started reading about MongoDB. You may have heard of MongoDB. Well, that's a type of document style. And a lot of times, especially with web apps and stuff, I have built apps where I go and I run a query in a relational database, I get back this result set, and then I need to go build a JSON, text file out of it because JSON, JavaScript object notation, that is the format that I'm going to give it to in the web to be able to do something with it. And so I'm forever taking JSON, converting that into an object in Java or whatever language, and then storing that in a relational database or getting it back and converting back. Well, a document style database says, forget the rows and columns of a database. What we store is JSON documents, right? So instead of writing SQL queries, you're going to say, go find me all the documents that have a child element called this, whose value is that. And what I get back is a bunch of JSON documents. So I'm not forever converting them back and forth. And so MongoDB was sort of the biggest one, but there's lots of different ones. In fact, I've got there's a pretty good. I used to use this NoSQL databases.org, something like that. This is very slow to load. This is probably the one. I remember it was getting very slow to load. No, NoSQL databases. I'm not finding the. You know what? Maybe just the Wikipedia will have categories, types, and examples. Okay, here. So it's very much an umbrella term with a whole bunch of, so here's key value stores, here's object databases, here's document stores. So in here, you'll see MongoDB somewhere, MongoDB, but also RavenDB, Google Cloud Firestorm, Azure Cosmos database, what else? Couchbase and CouchDB. So there's a lot of different ones out there that are document style. There's some that will store XML instead of JSON, things like that. In memory is an interesting one because most of these other databases ultimately store data on disk, right? And when you really need like microseconds, not milliseconds, we don't have time to go to disk, read from some blocks from disk into memory. We need to be able to just have some machines with big memory, and we'll query the data directly from there. And so there's a couple of popular open source databases for doing in memory. There's something called Memcached and something called Redis. And so these became very popular where we can say, hey, I'm going to query, and whatever my query is, we would do caching in front of the database. So Memcached, you would say, whatever the select statement you're going to write to my relational database, that's the key, and the result set is the value. So it's a key value store, but instead on disk, it's in memory, right? And so you would query this in-memory database with that select statement. If you got a hit, great, saves you a trip to the relational database. If you didn't get a hit, you'd go run the query in the database, get that result set back, store it in the in-memory database, and return it. So next time we did a query, we'd get a cache hit, right? So in-memory databases are really used heavily in caching. But again, they're usually just, some key, and then the result set is the value. Graph databases are very interesting. You've got things like Neo4j and there's a bunch of different kind of graph databases. The big idea of a graph database is instead of storing them in a relational database with rows and columns or whatever, you're actually storing data. You got these vertices and then the edges between them. So it's really good for like LinkedIn or something like that, where you need to find friends of friends, in that relationship. Trying to do those kinds of hierarchical queries, find me all my friends of my friends in a relational database, is a lot of self-joins to the same table. It's really ugly. In graph databases, there's certain kinds of operations that are going to be really easy to do. And so we use them. There's a lot of problems in computer science that when you think of it as a graph, then all of a sudden it becomes very simple. It's what's the shortest path between these two vertices, right? So imagine you could use that for networks, for driving directions, right? So the cities and then the links between them are the highways. And so you're trying to minimize for either distance or time driven or whatever. Trying to find what's the minimum spanning path, right? So let's say I'm a telco and I'm laying fiber optic cable to every house in town, right? What's the minimum number of lines I need to use, right? So sure, I can go from everybody to everybody, but that's overkill, right? So given this set of vertices, what's the minimum spanning graph? What are the minimum number of lines I have to put through to connect everybody? And so those kinds of queries become very simple in a graph database. Mm-hmm. Time series, this is when you're storing, data by, date time kind of values, and all your queries have to do with find me what happened between this time and that time. And so a time series database can do that nicely. Ledger. Yeah, ledger database. This is that idea that a good example is, say you have some industry organization, and you got a bunch of companies that are in this industry organization, and we need to keep track of something important. And the problem is somebody has to be the administrator of the database. So if one of the companies steps forward and says, okay, we can hold the database, how does everybody else trust that database? Because ultimately, with most databases, there is some ultimate DBA who is in charge of that database. And when they make changes to that database, there's some like log files and things generated. They could go hide what they did. They could remove all the log files. And so what we need is sort of in a zero trust situation where nobody trusts anybody, we need a way of showing this is exactly what happened in this database. And ideally, we can mathematically prove that these are all the transactions and no other transactions happened, right? So a ledger database is an immutable and verifiable history of all the changes to application data. Right? Now, one of the ways to mathematically make it work is to use blockchain, right? And in fact, that's going to be the quantum ledger database that AWS uses the blockchain to kind of prove that all these transactions that you see, those are all the transactions that happen. Finally, the last one here is the wide column store. Now, this is not the last of all the different kinds of NoSQL databases, but we're getting there. I mean, these are the main offerings. And the last one is a wide column store. A good example is Apache Cassandra. Now, I'm a Hadoop guy, so I used HBase, and it's another kind of wide column store. And what these things do is they say, instead of like relational databases where normalization comes in and you've got a bunch of different tables and they've got foreign keys and you're forever running joins SQL statements where I say, to get all the information I have to join this table to that table to that table so I can get all the elements. In a wide column store, you say, well, maybe I only have one big table or maybe just a couple really big tables. And so they're wildly normalized. You could have hundreds or even thousands of columns in this table. Now, when you think about relational databases, you're like, that sounds like a nightmare. There's going to be all kinds of sparse columns. The DBA is not going to be happy. Well, the way they're stored, it's okay, right? And so you might store the customer and all their orders. That's all one row in a table, right? So it's very, very fast at retrieval. It changes how things get stored. It really alters the application that's using it. And let me say this about NoSQL databases in general, right? In traditional relational databases, if I'm the DBA, I'm in charge of this data. I've got all these people running queries, insert, update, delete, select statements. I don't trust any of them, right? So we do a lot of heavy checks right here in the database. Referential integrity. You can't place a customer for can't place an order for customer 101 unless there is a customer 101 in the customer table, right? These data types have a size. You can't give me more data than that, right? You can't give me the wrong kind of data type. Also, the nice thing about that is I can go look at a relational database. I can describe the tables, and knowing nothing about the applications, I can probably run some queries and look at that data and do analytics on it. Right? All these NoSQL databases are a little bit more developer-centric. So if all you think about a database is, as a developer, I'm writing an application, at some point, I can't have this data in memory any longer. I need to put it somewhere because I'm going to run out of memory. If that's all you think a database is, well, then you just need a place to store it so that later you can access it quickly when you need to, right? And if you have no worries about anybody else looking at it, then you don't have to be able to look at this wide column store and figure out how to query it. It's really designed for this one application that's writing the data and then later getting it back. And so all the knowledge of what that data looks like and how it relates to one another is all in the mind of that developer who developed that app, maybe, right? So if you think of it that way, that's sort of the idea. And really it came out of the early days of relational databases. I'd say in the 90s, we started to see new kinds of databases. In MySQL, we We had the MyISAM database where we didn't have referential integrity. We didn't have null constraints. We didn't have all that. And it became very popular because when you had a web app, and I was going to go place a order for customer 101, there's no need to go and check that customer table and make sure customer 101 exists, because in my web app, I pulled the customer from a pull down list that I pulled from the customer table. So I'm not picking a customer that doesn't exist. The application already did that check. Why have the database check it again? And so we started to see relational databases where they kind of relaxed the database checking things and just said, your application is going to check it. No need to check again in the database. It's just going to slow down my database. And then we started to see these new databases coming along that didn't have any of that. And they were really just, I need millions of people to store and access data really quickly, right? And so we started to shift, what's the idea of a database? Now, it doesn't mean that the data in these things doesn't need to be analyzed at some point, but I may have a separate solution that grabs the data from there, puts it into a data lake so that we can analyze it later. Mm-hmm. All right, so we looked at the different style of databases. Now choosing the right AWS service really comes down to understanding what are the services. Right? One last thing before we get into the services, understanding what a managed database is. In AWS, they talk a lot about managed databases. If you're going to run, say, an Oracle database in your own data center, these are all the things you have to think about doing, right? You need the physical data center, you need power and HVAC and networking, you buy racks, you buy servers, stack them up in there. You have to maintain the servers, install an operating system, patch it over time, install the database, patch it, all that stuff. All falls on me. Now, the next level is I'm going to go get a virtual machine from my cloud vendor. So if I get an EC2 instance, Amazon takes care of everything up to and including the OS installation. I say, get me a virtual machine with this much CPU, this much RAM, that's running this flavor of Linux or this flavor of Windows. They install it, but I still have to patch it and install the database and everything. The next level is a managed database. So if I go and I set up Oracle RDS, so RDS is our relational database service. It supports about six different database engines. One of them is Oracle. You tell them what version of Oracle and whether you got your own license or you're getting one from Oracle. They'll do everything up to including they're going to patch the operating system. They install the database over time. They'll patch it. They'll take nightly backups. You can tell them when is the best time to take them. They'll set up high availability and set up a second database and set up synchronous replication between it. And I don't have to have all the DBA talent to do all that. I'm letting a brainless algorithm at Amazon do it. And so for some people, that's very attractive. Other people say, no, I'm doing the administration in a very specific way for a very specific reason, and I need to keep doing that. Well, then I'll just run it on virtual machines and do that part myself. But if you give over and allow Amazon to do more of it, well, then your total cost of ownership starts going down because we don't have to spend time managing a database. The chief technical officer at Amazon, this guy named Werner Vogels, he coined the term. He called it undifferentiated heavy lifting. It's the same work I have to do that you have to do to just get an Oracle database up and running. And he said, why not let Amazon take care of it? You're already trusting us to take care of the physical data center. Let us take care of the database. Now, you're still going to have to do the app optimization. You still decide what do the tables look like? Where are the indexes? What's the partitioning look like? And you have some decisions on the DBA, when to take backups, when's our maintenance window, so that if they do have to do some patching on the operating system or the database, when should they do it? Right? And so, we do want to look at these sort of fully managed databases to understand where that comes in. Okay. All right. Well, let's go practice a little bit. So let's say we have this bookstore application. Does that sound familiar? That's how kind of Amazon.com started. There's a lot of parts to this. It's a modern application. We've got a full stack web application with multiple use cases. So obviously there's a product catalog. I want to look at all the cookbooks or whatever. I need to be able to search by author, by title, whatever. We got this search bar. We want to push, here are the best sellers up at the top, right? And maybe some social recommendations, based on your past orders. Here's, books your friends have bought, things like that. right? So our first use case is the product catalog. Here's my business requirements. So we talked to Jane, the product manager, and she says, here are my requirements. I want to use a primary database to store and manage all the books. And when we're querying, we're querying by title or by category. I need to be able to load new books and modify existing ones. We don't really get rid of them. We may, just say that it's, very old or whatever. We have to store varying products per catalog. What I really need, though, is consistent response time at any scale. Right? And that scale, we know right now, we need to support a growth rate of 1 million products per year. Right? Then we go and we talk to the technology people. So here's John, our CTO. He says, what we really need is online real-time transactions, predictable performance at any scale, kind of what Jane was saying. He says we need read-write latency less than 10 milliseconds. And our peak right now is about 50,000 concurrent users. We want minimum downtime, durable writes, and scalable storage because we know we're going to keep adding more and more. So this is where we get to, here's the workloads that they gave us for this product catalog. So here's my access patterns, here's the data usage, consistency, availability, performance, all of this. And so based on all this, we have to look and say, what do we want? SQL or no SQL? Oh, this got messed up. It's already in there. Okay, so I'll let the cat out of the bag. It's no SQL, right? Relational databases don't have eventual consistency, allow semi-structured data. They generally can't respond in less than 10 milliseconds, especially as the scale gets big. Right? So we're going to end up with a NoSQL database and maybe a key value store, maybe a document style store, depending what we're doing. So that's where you may end up with. And so what are we talking about? In AWS, our key value style is DynamoDB. Our document style is Amazon DocumentDB. DocumentDB is, you can think of it, it's kind of a newer solution Amazon has that is really with MongoDB compatibility. So if you actually had, before you moved to the cloud, you had, MongoDB running somewhere on-prem. If you move to the cloud, without having to rewrite all your applications that are using the MongoDB API, now you can use DocumentDB instead. I guess what we're missing is this part where we have to tell them what are all the different AWS services. So for that, let me bring up the management console. If we view all services and scroll down to database, here's where we have the database. So for relational databases, we have one main service called RDS, the Relational Database Service. And this is a managed relational database. The first question it asks you when you go to create one is, well, which of these 8 database engines do you want? When Amazon first started, they started with what are the 2 most popular commercial databases? And at that time, it was Oracle and Microsoft SQL Server. It still is. And what were the 2 most popular open source databases? And that was MySQL and Postgres. Now, after a little bit of time, some customers said, we're using MariaDB that's sort of forked off of MySQL because we don't trust MySQL is owned by Oracle. And so they asked, hey, can you support this? And they said, oh, yeah, we can do that. And then more recently, a bunch of big customers were moving a bunch of stuff that was written to talk to IBM DB2. They said, can you support that? And they said, yes. And so these are the 6 kind of major engines that Amazon RDS supports. Then you can imagine, like, say you pick Oracle database and you go down here, and depending which version you pick, you can either bring your own license if you've already got a license with Oracle, or say license included. Well, now my hourly rate for this thing went through the roof because I pay my bill at the end of the month to Amazon, and then they turn around and pay Oracle what they're owed for these licenses. Right? And Oracle licenses are not cheap. Right? So for both SQL Server and Oracle, Amazon was starting to get a very good picture of how much are their customers paying for these commercial databases. Now, it's true that those commercial databases get very good throughput and scale compared to the open source things. Now, I can make MySQL scale. I just need a lot of good DBA talent to set up MySQL cluster and really tune it properly. Right? It doesn't mean you can't get there. but Oracle and SQL Server make it easy to get the throughput and scale you want for enterprise apps. And what Amazon said was, what we'd like to do is build a relational database that rivals Oracle and SQL Server, but at like a tenth the cost, because we know how much people are spending. So they decided to come out with Aurora. Now, here's the problem. People are very wary of this, right? You can imagine, I've been dealing with Oracle for 30 years, and I know it's very expensive. And every 18 months, they're going to tell you, oh, your old version is no longer going to be supported. You need to upgrade to the latest version. And you're like, ugh. And I'm kind of stuck because each database vendor has a slightly different SQL dialect. SQL is not a hard standard. You learn SQL for Oracle, then you go switch to MySQL, and there's some slight differences. So you have to go rewrite all your queries in all your applications, right? And so that's that vendor lock-in a little bit, right? Now, Postgres is probably the closest to ANSI standard, but each one of them has slightly different variation. And so people said, I don't want to get locked into just Amazon's database instead of Oracle. So Amazon said, hold on. We don't want that either. Well, we don't say we want that. But what we'll do is this. When you use Aurora, you can either get one that is MySQL compatible or Postgres compatible. What do we mean by that? Well, if I pick this Amazon MySQL compatible, then the applications I write to connect to this, they're going to use the MySQL drivers. They're going to use the MySQL SQL dialect. So for all intents and purposes, that application I wrote that talks to Aurora thinks it's talking to MySQL. So if I ever want to move this application outside of Amazon, put it somewhere else, I just have to figure out how to make a MySQL database scale and perform the way we need it to, right? And so that was how they avoided vendor lock-in and offered a good database at a much cheaper rate. And it was very effective. A lot of customers moved over, right? We saw a huge exodus from Oracle towards Aurora Postgres in particular. And it, started a huge feud between a couple of billionaires that was hilarious. Some good stuff came out of it, I think, too. But, so that's sort of the RDS database. I just wanted to mention that. If I go back to all services and I look at the relational databases, the other relational database we have in addition to RDS is our data warehouse. They have that down here under analytics. So Amazon Redshift is a relational database, but it's one that's more geared towards data warehousing than regular kind of database stuff. So that's our two relational database options. Beyond that, what else do we have? Neptune, this is a graph database. QLDB, that's our quantum ledger database. So it's a ledger database. DocumentDB, this is a document style database with MongoDB compatibility. Right. Keyspaces, that's a wide column store with Apache Cassandra capability, capability sort of thing. TimeStream is a time series database. Amazon MemoryDB is an in-memory database. It uses, it's basically using a version of Redis, but it also has the storage side. We do have Elasticache, which is really an in-memory database. It's got two different underlying engines. One is Redis, one is Memcached. And then DynamoDB was the first and sort of most powerful NoSQL database that Amazon came up with. And it's been around for a long time. It's either a key value store. It also has some capabilities that can make it kind of a document style store as well. And it is wildly popular. It is serverless. I just set it up. Here's what I do when I create a DynamoDB table. I click on DynamoDB and I say create table. I give it a name. I tell it what the primary key looks like, and then that's it. That's all I have to do. There's some other settings, but it's got a lot of good default settings. And all of a sudden, I can start inserting into it. I can insert millions and millions of rows. I never think about the underlying infrastructure. It's very much serverless. When I launch an RDS database, I do have to think a little bit about, am I going to, what's the underlying infrastructure a little bit? But here, it's very much serverless. Right? So that's the big list of the AWS services and how they map to those styles that we saw. Oh, I think I've got a question in the Q&A. Yeah, I've seen this question a couple times. We're going to come back to that, the security question. I've seen it. I'll get to it. All right. So this is product catalog. That was our first use case. Here's another use case. We talked to Jane again, and she says, "Okay, I want to be able to do the top 20 purchased products. Display that list on your homepage, and show like near real-time results. So as it keeps changing, right? So what do I need? I need a near real-time analytics solution for leaderboards, ultra low sub-millisecond response times. So as soon as you see that sub-millisecond, you're thinking, no time to talk on disk. This is in memory. Right? I need scalable and predictable performance. And then they tell us how many, mostly reads, not that many writes per second, but a lot of reads per second. Right? So we fill this all out. What do we end up with? Read latency, sub-milliseconds. We need to really scale the reads. Eventual consistency is fine. Top end order, books by order. So this sounds like it's a NoSQL option. In particular, I mentioned that it's probably an in-memory option. Right? So maybe Elasticache either for Redis or for Memcached. Redis tends to give us more options for, if I need to sort the things coming back or whatever. Here's another one. We talked to Jane again. She says, well, I need recommendations based on social context and what products you bought, what your friends bought, that kind of thing, displayed on the homepage and on the product details page. And again, we want this to scale with more products, users, web pages. Right? Talked to John about the technology side. He said, well, we need high quality recommendations in real time, traverse highly connected entity data sets. Right. So this user has these friends and here's what they bought, predictable performance. Tell us a little bit about that. When we fill this all out, what we find is we're querying products bought by users' friends, other products similar to this product. That's the two different kinds of patterns we're doing. Again, neither of these lend themselves well to a relational database. Sounds more like NoSQL. And what kind? Well, whenever you think friends of friends or products that are like other products, you should probably be thinking, sounds to me like a graph database. Mm-hmm. Now, can I go set up a bunch of virtual machines and install Neo4j, a very popular graph database? Yes, but more likely, we're already in AWS, right? If we're building a greenfield application, we don't have code written according to some existing graph database. Well, then we're going to probably use the nice managed database that Amazon provides so that we don't have to do any of the administration. And that's where Neptune comes in handy. Right? So if we take that all into account, now we're looking at something like this. Our Bookstore application starts to look like this. So you come in, our web app is, a bunch of static pages in Amazon S3. We use CloudFront in front of that. That's our content delivery network, right? And Cognito maybe to keep track of users and things like that. The API gateway takes me to a Lambda function where we're either sending, queries to DynamoDB or to Redis for the in-memory stuff or to the graph database. Possibly our search is done maybe through OpenSearch service. We didn't talk about that. OpenSearch is the newer name for Elasticsearch. Elasticsearch is a popular open source sort of search kind of database, but the company Elastic started to push their weight around too much in the open source community. And so Amazon and some others said, forget it, we're going to fork off of that and make a new OpenSearch. And so this is their service to manage that. So you get the idea that depending on the microservice, each Lambda will talk to different, back-end things to do whatever they need to do. All right. We're basically at the end of this slide. It's good because we're at our hour and a half. Just some quick questions, and maybe you can throw your response in the chat, A, B, C, or D. We have an architect who's designing a database solution that requires strict entity relationship constraints. Which database category should the architect explore to meet this workload requirement? strict entity relation constraints. So I think what we're talking about here is, yeah, a few people have responded. C, a relational database, right? Where we have these entities, customer, order, product, and then we've got the relationships between them, and we want to enforce those, right? That's where relational databases really come in handy. Now we have an architect that's designing a database that requires strict entity relation constraints. Which database category? Oh, yeah, sorry, that's the same. Here's the next question. We're planning a database solution that is immutable for bank transactions. Which database category should the architect explore? Okay, we got some people answering D, ledger database. Yeah, that's the immutable thing, right? So everything that happens, we can't undo any of them, right? If somebody made a mistake and they said, oh, I deposited this check, but we got the number wrong, well, then we'll just do another transaction that backs that out and or whatever, right? So we don't get rid of anything. We make a new entry that does the opposite. So a ledger database is good at this kind of thing. How about this one? Analyze the business requirement of an application workload, including availability, durability, capacity, scaling. What other business requirements should we think about when selecting the right purpose-built database? Select two. So we looked at availability, durability, capacity, scalability, and compliance probably doesn't make sense just because, well, actually it does, right? So we may have some databases that have strict requirements, and so we may have to look and see, does this database service, has it been vetted for PCI compliance or something like that? So yeah, I would think maybe we better consider compliance. We didn't mention performance in here, so maybe performance. Service quotas are a thing that you can always change, right? So when you first set up an AWS account, there's a whole bunch of quotas. The first quota you run into is you can only run 20 virtual machines in a region. You're probably going to change that. It's just there so you don't shoot yourself in the foot when you first start out, but you just go fill out a form and say, hey, I need to increase this. So that's not a concern. Access control, all these databases have hook into identity and access management to say who's allowed to do what. Customer support, I mean, you're providing support to your customers. Amazon supports all these things. Yeah, so I think it's just A and B then, if they want to. A and B. All right. Okay. So next steps, where to go from here. Right? Well, one suggestion is we have a 3-day class called Planning and Designing Databases. Takes this hour and a half, blows it up over 3 days, gives you lots of labs where, first we're dealing with relational databases on day 1. Day 2, we start getting into DynamoDB, key spaces, document DB. We do an activity where we choose the right database. And we actually have one where we do work with DynamoDB. Then we learn about some of the other ones, an activity where we talk about caching, another activity where kind of like look at all the different elements of this app, and we have time to actually go through it. And then they've got a nice little lab on Redshift as well. Those are the 3 most popular databases: is RDS, DynamoDB, and Redshift. So those are the ones we get you to lab. Question, are we going to get the slides presented? Unfortunately, I'm not allowed to share the slides, but you will get the recording of this. Okay? So let's go back to the question that we had. Who takes care of the database security, column encryption for sensitive data, all that kind of thing? Well, it turns out that, in transit, we usually just deal with, transport layer security, right? So I can set it up and say, hey, when I create an RDS database, when somebody connects over JDBC or ODBC, they have to connect, using SSL. And by the way, here's the SSL certificate we give to the client so that they can make that connection, right? So in transit, we deal with SSL. At rest, wherever we store data in AWS, meaning any of these databases, we always have the option of server-side encryption. And they got a couple options. The biggest option is KMS, the Key Management Service, where I can go and say, I need an audit trail, so I want to be able to generate the keys used to encrypt all the data, and it gets stored there. And it's sort of this envelope encryption where this master key is something that I can rotate. I can decide when to rotate it. I can go into CloudTrail and get an audit trail of when were these master keys used by whom and when were they rotated. And that's exactly the kind of information I generally need for whatever compliance body I'm talking to show that, hey, we're doing server-side encryption and everything's encrypted at rest and it fits all those things we need. Now, there's a lot more to database security than just encryption at rest and in transit. There's all the network side of things. I'm running this database in a VPC. Well, I've got all these different firewalls. That's all on me. Those firewalls exist, but it's up to me to make good rules, right? So it all comes back to that shared responsibility, right? Amazon gives us some of the tools. We better use them properly, right? So, okay. So I think we're done with those ones. I'm just trying to look and see if I missed any other questions. I'm sticking around for a little while if you have questions. I do want to flip back to my slides and show you a couple of other things coming up. Where to go next? If you're really new to AWS, you might want to take, a one-day Tech Essentials class or one of the 3-day classes. These are the two most popular 3-day classes, Architecting on AWS and Cloud Operations. The Cloud Operations is a little more geared towards, somebody who's like a Linux or a Windows administrator, right? And it'll teach you the basics of, launching all kinds of stuff, not just databases. Architecting is just a little bit higher level for architects, developers, anybody other than heavy-duty operations people who want a good broad view of AWS. Those would be good places to start. If you already have that knowledge and you want to delve deeper, there's that 3-day planning and designing databases. We have one coming up in August 26th, and then the next one's in October. So this is a class that only runs, every couple months, whereas the architect is something we run probably every 2 weeks or something like that. Also kind of related to this is the data analytics side of things. So building a data pipeline that says, hey, we're grabbing log files or whatever, dropping them into S3, then we take them and massage them, put them into a data lake, maybe pull a subset of that into a data warehouse, all that kind of data engineering side of things. We have a 4-day class called Building Modern Data Analytics Solutions. It's actually made up of 4 one-day classes. So if I click on this, I get to here and I can view the full schedule. So there, September 17th or whatever. If I look at the actual, get out of here. If I look at what makes it up, here it is. It's these 4 one-day classes. So it starts with a 1-day class on building data lakes that covers the services lake formation, S3, and AWS Glue. Then the batch data analytics. This really covers Amazon's Hadoop, which is called EMR. And then building streaming, this talks a lot about Kinesis and Amazon MSK, and then a 1-day class on Redshift. So you could take any of these 1-day classes. If you look, the first date coming up, September 17th, that's the first day of that 4-day class. So that's the difference of databases of AWS from AWS competitors. Oh, yeah, that's a good question. If we look at these databases, something like DocumentDB, it's a fully managed document style database that's compatible with MongoDB. Well, MongoDB is just an open source tool you could run on-prem, you can run in any cloud. I can run it in AWS by just getting a bunch of virtual machines with some storage and then installing it and managing it all myself, right? So there's a lot of, popular databases, and then the AWS service is just helping us with that, right? But if you look at, say, Microsoft Azure, they have a lot of the same stuff. They have something called Cosmos DB. Their Cosmos database is a lot like DynamoDB, but also it has different, they use one service name and it's got a couple of different styles underneath it, right? If you look at something like Redshift, this is our data warehouse appliance. Well, all the cloud vendors have something like that, but also another competitor is Snowflake, right? They have this kind of an idea of a data warehouse. They have different ideas. In fact, they had some really good ideas that changed how all the other cloud vendors built their data warehouse appliances, right? So it's hard to, compare and say this one's better than that one. I mean, as soon as you read any of kind of comparison, you have to look and say, well, who's making this comparison? Because chances are, that was sponsored by somebody from Amazon or Azure or whoever. So I think it's very difficult to talk about the differences of databases from AWS from its competitors. I think AWS has the broadest set of databases. Like RDS supports, we saw, now 8 different options when you create a database. If you go to Azure, well, of course, they're going to support Microsoft SQL Server and maybe some open source Postgres and stuff, but they don't have as many other options because they are sort of, Microsoft centered. If you look at Google Cloud, they have their own stuff. So they got Bigtable, they've got Spanner. When it comes to a regular database, they've got their own. They don't really get into that game of, well, hey, I want Oracle. Well, you can run Oracle, but they've got some options for that. So, I think that there's sort of, I would say that Amazon has the broadest set of database options, both from a relational database, RDS style, and the different engines they have, and from the NoSQL options. They have more than the others. Whether or not, particular service from A is better than B, I think you have to go test it out yourself. I mean, I'm usually a little more biased towards AWS because I think they do a pretty good job on most things. And I think that their overall product is, more highly available and stuff than others. So if you are interested in taking any of these courses, there is a promotion that we have on right now. Let me put the link to that promotion into the chat. So you can click on that and read about it. I think you have to, here's the code, Upskill 500, and you have to register and I believe take the course, register and complete the course before August 31st. So if you're taking a class in the next month, you can get up to $500 a day, up to $500 off the class. It's basically $100 a day. So if it's a 3-day class, you can get $300 off. Of course, if you don't like any of the schedule that you saw for dates of whatever course, just talk to your rep. You're going to get an email follow up with the recording, and it'll tell you who you can contact if you have questions about sales. But if you have maybe 5 or 6 people or more, more than 6, you're going to get a better deal than just individually, going into our public classes. There's some economies of scale there, but also you got a lot more. We can put up a date just for you. We can do it, maybe you're on the West Coast or in European time, we can tweak things. Sometimes we'll do a 3-day class in sort of 5 half days or something like that. You got a lot more flexibility when we do private training. And so our promotion, we'll give you up to $500 per day off on private training as well. Mm-hmm. Last thing to mention is next Wednesday and the following Wednesday, we've got a couple more, our Wednesday sort of 1 till 2:30 kind of free discovery days. We're done sort of the data ones. The next 2 have to do with generative AI. So the next one's just kind of a very high level for business and technical decision makers. And then we've got one that delves a little deeper into prompt engineering. Okay? But still, you don't have to be some, genius at AI or anything like that to take that one. That'll just teach you good techniques for whether you're just using ChatGPT on your own to do whatever, right? So good stuff in there. All of these discovery days, everything you can find if you just go to our, actually, if I just go to the AWS, yeah, right here. Let me put that URL into the chat, and you'll find our actual classes and our free discovery days there. The actual classes are in these accordions. So if you're looking for the architecting class, you'll find it in there. The discovery days are down at the bottom, and these are the free ones. So the 2 coming up are the generative AI. So if I view that one, you see free, hour and a half, guaranteed to run. You just go in and enroll. If you're enrolling in a regular class, this is where you would put that promo code Upskill 500. Okay, so hopefully you grab those 2 links that I just put in there. That's the main stuff I wanted to say. Last little bit about the company ExitCertified. We do a lot more than just AWS. We're partnered with all the different cloud vendors. So whatever the official courses from that vendor are, we've got them. But then beyond that, we've got a lot of cloud related stuff. So analytics, machine learning, AI, private cloud stuff. So VMware or OpenShift, all those kinds of things. If you're looking for more of like a cloud agnostic kind of security, because you're moving towards some certification, maybe the Security Plus from CompTIA or the CISSP or one of those kind of ones, we got that. If you're going to do cloud native stuff with Docker and Kubernetes, microservice architecture kind of concepts, we got a lot of that. And so this is our cloud centrics diagram. Actually, let me, oops, what happened there? I was going to click on this diagram and I think that opens up yeah, I'll put this URL into the chat as well in case you're interested in looking that up. This diagram on our website is very functional. Like, so if I click on Kubernetes, it takes me to a page where we talk all about our Kubernetes offerings, and you can get in there and you see a bunch of Kubernetes for developers or Docker and Kubernetes fundamentals and, so on and so on. Yeah, so that's, I think, the main things I wanted to say. Like I said, I'm going to stick around and see if anybody has any other questions, but let me stop sharing. I did put my email address in at the beginning. I guess if you joined after, let me throw my email address in one more time. And like I said, you should get a follow-up email with the link. I think that'll come tomorrow to the recording. Otherwise, hope to see you in another webinar coming up or even in a class coming up. Thanks for attending. I think we still have some people here, but like I said, I'll stick around if there's any questions. Otherwise, hope to see you soon. Great. Yeah, I talked a lot in an hour and a half. I'm going to shut it down.